Today we're digging into a paper called Training Foundation Models on a full-stack AMD platform, compute, networking, and system design. And really, it's more than just a paper. It's basically an operational manual, proving out a whole new hardware ecosystem for frontier AI. All right, let's do the 1-minute hook. This work is the first report on a large-scale mixture of experts, or MoE, pre-training study done completely on the AMD MI300X GPU and their Pollara Interconnect. They're basically confirming that this entire stack is production-ready for massive training jobs. The model they built, ZAYA1 base, has 8.3 billion total parameters, but only 760 million are active at any given time. And it's built on a new architecture they're calling MoE++, which uses some cool new tricks like compressed convolutional attention and a really expressive router.
And the results really validated the entire approach, not just the hardware. I mean, ZAYA1 base went head-to-head with leading models like Qwen3-4B and even managed to outperform Llama 3-8B on reasoning, math, and code. That's a huge proof point for both the hardware stack's maturity and their new MoE design.
And to get there, the engineering effort was just heroic. They did this incredibly systematic cluster characterization, developed specific sizing guidance for transformers on the MI300X, and they even built custom kernels for their optimizer and LayerNorm. Plus, they built an in-house fault tolerance system called Aegis. All of these system-level wins were what made stable, high throughput even possible. So, let's unpack that. The core mission here seems to be about understanding the practical realities of training at scale on AMD. For you, the researcher or developer, why is this breakdown of the MI300X so vital right now?
Because the dirty secret of LLM training is that your final model quality is completely bottlenecked by your cluster's throughput and, maybe more importantly, its stability. For years, scaling has just meant one thing, one vendor stack. If you wanted to go the AMD route, you were basically flying blind on how things like large-scale collective communications would perform.
So this paper is filling a massive knowledge gap for the whole industry.
Exactly. It's a two-pronged attack. Systems and modeling. On the system side, they just needed to get the detailed measurements. This is the first time anyone has benchmarked Pollara collectives at this scale. They wanted to figure out where time and bandwidth go and, how you can port a mature NVIDIA pipeline over to RSCM and RCCL without a huge performance hit. It's really a handbook for that migration.
And the ZAYA1 model is kind of the final exam. Its success proves the whole co-design stack is truly ready. Okay, let's get under the hood of the cluster itself. The node architecture looks pretty beefy. 8 MI300X GPUs, 2 terabytes of DDR5 RAM, and a dedicated 400 gigabit Pollara NIC for every single GPU.
Yeah, that's a serious investment in communication. And they made some interesting choices there. For the network, they didn't go with a classic fat tree or close topology. They used what they call a Rails-only topology.
Okay, what does that mean in practice? Rails only.
It's a cost-saving measure, mainly. You use fewer expensive switches. But the trade-off is path diversity.
So you have fewer ways for data to get from point A to point B.
Exactly, which means you have to be almost obsessive about mapping your model and data parallelism to the physical layout of the cluster. If 2 GPUs on different rails need to talk, that traffic takes a longer path, and you get a performance penalty.
So the software has to be smart about the hardware it's running on.
You're trading hardware simplicity for software complexity. And they also did something else smart. They separated the networks.
Right, the training traffic from the operational stuff.
Yes, 2 physically separate networks. The super fast Pollara fabric for all the gradient communication, and then a 200 gigabit VPC network just for I/O, checkpoints, loading data.
So a big checkpoint write doesn't suddenly cause your training to lag.
Never. That separation is, that's the mark of a real production-grade system.
Okay, let's zoom in on the GPU. HBM bandwidth, the MI300X, hits 4.330 terabytes per second. That's a lot. What does that speed actually buy you in an LLM?
It's a game changer for any memory-bound operation. Think LayerNorm, or attention with shorter sequences. These aren't limited by your tensor cores. They're limited by how fast you can shovel data in and out of HBM. The paper found the crossover point, where attention becomes compute-bound instead of memory-bound, is surprisingly high. It's somewhere around a 4K to 16K sequence length.
Wow. So if you're running at a typical 8K context, you're still bottlenecked by memory speed, not compute. That MI300X bandwidth is a huge advantage right there.
Absolutely. Now, on the compute side, the GEMVAMs, the matrix multiplications, this is the real workhorse. Their analysis found something critical for anyone working on this hardware. To hit peak throughput, your problem size needs to be about 200 GFLOPs.
Wait, so if I'm a developer and my matrix multiplication is, say, 150 GFLOPs, Am I just losing a bit of efficiency, or is it worse?
Oh, it's much worse. That 200 GFLOT number is the threshold to fully saturate the hardware. Fall below that, and you're leaving a ton of compute just sitting idle. It's like having a race car and never taking it out of first gear.
So you have to be really deliberate about sizing your model's layers.
You have to. Their solution was to generate static lookup tables that map your tensor sizes to the most performant algorithm in RockBLAS at runtime. It's that systematic.
Okay, finally, inside the node, the Infinity Fabric, or XGMI. You said this is totally different from ND-switch.
It's a critical difference. With XGMI, to get the maximum bandwidth, all 8 GPUs have to be participating in the collective operation.
Why? Why does it drop so much if only, say, 4 GPUs are talking?
Because the fabric is designed to spread the load across the whole mesh. If only half the GPUs are in on an all-reduce, the other links are idle, and the data has to travel a less efficient path, the numbers are stark. They got almost 300 GBs with all 8 GPUs, but dropped to 4 GPUs, and that plummets to around 140 GPUs.
Your parallelism strategy has to be all in on the node.
Either that, or you find a way to avoid those collectives entirely. It completely dictates your design choices.
All right, let's pivot from the hardware to the model they designed for it. ZAYA1 base, their MOE++. What makes it plus?
3 big things. First is Compressed Convolutional Attention, or CCA. This is how they do sequence mixing, but it all happens in a compressed latent space. And this isn't a small tweak. It massively cuts down compute for training and prefill, and they got up to an 8x compression on the KV cache.
8 times smaller KV cache. For anyone working with long context, that's huge. Suddenly, serving a 32K context model at scale becomes practical.
It turns it from a research idea into a deployable product, exactly. The second big piece is the ZAYA1 router. They ditched the standard linear gate for a small MLP, which just gives it way more expressive power.
And the routing decision itself is different.
Yeah, they use something called exponential depth averaging. So instead of each layer's router acting alone, it mixes its scores with the routing decisions from the layer before it.
So it has some context, some memory of where tokens have been routed already.
Exactly. It promotes better expert specialization and keeps the load balancing more stable. They even use a PID controller-inspired scheme to manage it.
And this led them to a really contrarian choice. Top 1 routing with no residual experts. The whole industry is moving to top 2 or higher for stability. Why did they go the other way?
Because the router is just that good. It's so expressive and context-aware that it becomes highly confident in its choices. The entropy is low. If the router is 99% sure that expert A is the right choice, you don't need to waste compute sending that token to a second best option. It lets them be extremely sparse and efficient.
A fascinating trade-off. And the third piece, residual scaling.
This is a really lightweight trick. They just apply a learned bias and gate directly to the residual stream. It adds almost no parameters, but gives them explicit control over the information flow and stops the residual norm from exploding, which is a common problem in deep models.
So looking at the training, they went for 14 trillion tokens in 3 phases, including that big context extension to 32K.
And that CCA architecture was absolutely essential for that jump. That 8x memory reduction meant they could go to 32K without needing crazy parallelism schemes just to fit the activations in memory. Plus, the MI300X has a massive 192 GB of HBM, so they could mostly stick with a simpler data parallelism using 0-1, which only shards the optimizer states.
And speaking of optimizers, they used Muon. How did that help with memory, especially since MOE models are so hungry for it?
Muon is based on SGD with momentum, so it only needs to store 1 extra term, unlike AtomW, which needs 2. But the real challenge with MOE is that you need enormous global batch sizes. They went up to 30 million tokens.
Why so big?
Because each expert only sees a fraction of the data. If your global batch is 16 million tokens and you have 16 experts, each expert only sees a batch of 1 million. To keep that number high enough for stable learning, the global batch has to be huge.
Okay, let's get into the deep systems engineering. The paper really is a survival guide.
Yeah.
What were the biggest software bottlenecks they had to smash through?
Ironically, their custom Muon optimizer was a huge latency bottleneck because of something called Newton-Schultz iterations. It involves a lot of repeated matrix multiplications to form a gram matrix, so they built a custom symmetric matrix multiplication kernel.
Wait, why does symmetry matter so much here?
Because a Graham matrix, which is 6x Leller, is always symmetric. A standard multiplication kernel computes every single element. Their custom kernel knows it's symmetric, so it just computes 1/2 and avoids all the redundant calculations and writes. It basically cut the arithmetic work for that step in half, a pure 2x speedup.
That is a beautiful low-level optimization.
Yeah.
What about something more standard, like LayerNorm?
Yeah, a naive port to ROCm just didn't perform well, so they had to write their own fused HIP kernel. It combines the residual add, calculating the stats with Welford's algorithm, the normalization, and the final affine step all into a single GPU operation.
We all know fusing is good, but just remind us, why is that so much faster?
It's all about memory movement. In a naive version, each of those steps writes its result back out to the slow HBM. By fusing them, the data stays in the super-fast on-chip SRAM, or registers for the whole sequence. You avoid all those expensive round trips.
They also had to fix the distributed Muon implementation for 0-1. What was the problem there?
The default implementation, when sharded, used a massive all-gather operation to reconstruct the full gradient matrices. It completely defeated the purpose of sharding in the first place, memory-wise. Their fix was brilliant. They replaced that all-gather with a simple, low-volume send-rec-rev exchange that only communicates the little bits of the parameter shards that sit on the boundary between two GPUs. It cut peak memory way down.
And what about their unique CCA attention? Did that require a special communication scheme too?
It did. Since it uses convolutions, they needed a new kind of ring attention. Before the convolution, they do a very small point-to-point exchange of just the tokens on the edge of each chunk. Then an all-gather for another component. It's a custom communication pattern designed specifically to keep network traffic minimal, even at 32K context.
Let's talk stability. That's the silent killer of these huge training runs. Their checkpointing trick with the 1 TB page cache seems like a stroke of genius.
Oh, it is. So they do distributed checkpointing, but by jacking up the node's page cache, recent checkpoints aren't just on slow disk, they're sitting in RAM. The Linux page cache even persists after the program restarts, so recovery from a soft failure is nearly instant. It's like building a high-speed undo button into your cluster.
And the final safety net, their Aegis fault tolerance system.
Aegis is what lets you sleep at night. It's an automated system that watches for all the common painful failures, NIC errors, GPU hangs, even weird loss spikes that might signal silent data corruption. And it just runs the playbook. It'll reboot a node or restart a NIC without a human having to wake up at 3 a.m.
So after all of that incredible engineering, did the model actually deliver? Did ZAYA1 validate the whole stack?
And then some. ZAYA1 base, with just 760 million active parameters, performed on par with much bigger dense models like Qwen3-4B on core reasoning, and it flat-out beat Llama 3-8B and other small MoE models.
So you get high performance, high sparsity, and low latency all on this new stack.
Exactly. And the fact that their mid-training checkpoint was already approaching state-of-the-art reasoning before any fine-tuning shows that this MoE++ architecture is exceptionally good at learning complex tasks early on.
So the big conclusion for the industry is pretty clear. The AMD Stack is mature, it's robust, and it's ready for competitive large-scale training.
Absolutely, as long as you embrace the hardware. The success here came from treating things like the 200 GFLAB gem in size and the behavior of XGMI and design constraints as first-class citizens in your model design, not as annoying bugs. That systematic, measurement-driven approach is the key to scaling any frontier model, no matter whose hardware you're using.
So what does this mean for you, the developer or researcher? It means you have a validated, open alternative in the hardware space, and you have a detailed blueprint for how to optimize for it.
And if we zoom out to the bigger picture of MoE design, this work really puts a critical trade-off into sharp focus. ZAY1 proved you can get incredible performance with a super smart router and top-1 routing. It maximizes your efficiency, which really makes you question the current trend of using higher top-K routing just for stability. Is that really the best path forward? Or should we be putting more effort into building smarter, more confident routers like ZAY1s so we can achieve greater efficiency through maximum sparsity? It kind of suggests we might be over-provisioning our models just to compensate for dumb routing.